Hi, I'm Benny, and I've dedicated my life to understanding the universe, with the hope that one day I'll get the chance to hop on a rocket and see it for myself. Growing up, I was always looking up, not just at the stars, but at the endless questions they sparked. I'd spend hours wondering what was out there, how it all worked, and if I'd ever get the chance to see it for myself. This is SpaceBites, where I take the overwhelming, mind-bending world of space and break it down into small, easy-to-digest pieces. Think of it like snacking on the cosmos, quick, simple, and deliciously full of wonder, so anyone can understand and enjoy it no matter their background. Why? Because every atom in your body was forged in the heart of a star. The carbon in your DNA, the oxygen you breathe, the calcium in your bones, all of it began in stellar furnaces, which means, quite literally, the universe is in you. You are the product of cosmic alchemy, billions of years in the making. The same processes that built galaxies also built you, linking your existence to the cosmos itself. Before there was something, there was a whole lot of nothing. And out of that nothing came everything. Today we're diving into one of the most mind-bending ideas in cosmology, which is called inflation, when the universe expanded faster than the speed of light itself. In that very, very short amount of time, the seeds of every galaxy, every star, and eventually us were planted. So how can nothing give rise to everything, and what does inflation tell us about the beginning of our universe? If we look at the timeline of our universe, then the hot Big Bang, which is this fireball of plasma or cosmic soup that eventually cooled into atoms, stars, and galaxies, actually comes after inflation, where the inflationary energy decays into particles and radiation. And that moment is what we call reheating. Hello everyone, and welcome back to another episode of Space Bites with Benny. It's me, Benny, your favorite nerd. Today we're diving into the fastest moment in the history of everything. A flash so quick it makes a blink feel like an eternity. And we're talking about cosmic inflation, the moment the universe grew from subatomic to cosmic in a trillionth of a second. But first, I will read to you two poems, both called Cosmic Inflation, to start us off. One is by Monica Beaujean, and it's this dreamy, free verse reflection on how the universe expanded from a single point into, well, everything. And she has this haunting line where she says, "Forevers are real," that really captures the mystery and vastness of everything. It feels more emotional than scientific, like she's trying to grasp infinity with language. The other one is by Kate Rauner, who is actually a former engineer and sci-fi writer. Her version is more structured and rooted in the science, and she touches on the Big Bang, the cosmic microwave background, which you should already know what it is, and how inflation shaped the universe's layout. It's almost like a lyrical explainer wrapped in rhyme. They both have different styles, but both poems try to make sense of this mind-blowing moment in cosmic history. And they remind us that even equations have poetry in them. Here is Cosmic Inflation by Monica Beaujean. I know ghosts and they're made of light. Mountains are just the bones of earth, and my skin is just the artificial border between me and infinity. When did moon get so mean? When did sun learn to spit its rays, instead of merely pour? Forevers are real and they exist in my hands, nevers are real and they exist in my feet. I talk, yes, I talk, but my tongue makes my words sound like popping balloons, so lively, so hollow. He said I am overreacting, and I told him so was the universe when it went from a dense singularity to this. Here is another poem, also titled Cosmic Inflation by Kate Rauner. Since Penzias and Wilson chased the pigeons off their dish and listened to the sound of the cosmic hiss, the Big Bang's been our vision of the moment of creation. Now we have the signature of cosmological inflation. What the human eye can see is just a fraction of creation, but we can build a telescope to view the radiation. Patterns swirling in the light where gravity flows through could unite relativity with the quantum view. Space itself expanded faster than the speed of light. We still need confirming work to prove the study right. But Einstein's great mistake seems more and more correct. Could dark energy be its remains? That's what we'll puzzle next. It won't change my life tomorrow, won't put cream into my tea, but knowledge is always better than ignorance can be. And my favorite part of this poem is the charming, grounded reflection at the very end that even if this cosmic story doesn't impact your morning routine, it won't put cream into your tea, the pursuit of knowledge always makes life richer than ignorance. I mentioned before that inflation was the expansion of the universe, and you may have wondered, but how can anything go faster than light? Isn't that kind of against the rules? It would be unless you're not moving through space, but you're expanding the fabric of space itself. I'm going to say that again. So, if I say that inflation was the expansion that happened faster than the speed of light, and you say, but how can anything go faster than the speed of light? That's against the rules. It's okay unless you're not moving. It's okay only when you're moving through space, when you're actually expanding the fabric of space itself. And this single tiny moment, called inflation, holds the key to some of the biggest questions in science. For example, why does the universe look the same in every direction? Why is it so flat, so balanced, so stable? Why does it seem to have no overall motion relative to the ancient light that fills it? Here I refer to the cosmic microwave background. And where did the first stuff in the universe actually come from? So, let's start off by putting it into some context. Let me talk a little bit about the timeline of the universe. At the very beginning is what we call the Planck time. This is the smallest measurable time interval. Physics as we know it breaks down. Gravity is not yet unified with other forces, and here we need quantum gravity to be able to describe it. After Planck time, we have what we call the grand unification epoch. This is when gravity separates from the other three fundamental forces. Here I refer to electromagnetism, the weak and strong nuclear forces. And grand unified theories describe a single force that merges the strong, the weak, and the electromagnetic interactions. And here's where we talk about inflation, or we talk about inflation as being a field, a scalar field called the inflaton. And this dominates the universe's energy density, and it causes exponential expansion that smooths and flattens space. After inflation, we have reheating. This is when this scalar field, this inflaton, decays, it breaks down, and it repopulates the universe with particles and radiation. When I say radiation, I'm talking about light particles, so photons. And this marks the beginning of the traditional Big Bang model that you may have heard about previously. After reheating, we have the quark-gluon plasma. This is when quarks, the fundamental building blocks of everything, so quarks make up particles like protons and neutrons, along with gluons, and you can kind of think of gluons as the glue that keeps these quarks together. And leptons are another type of fundamental particles, for example, like electrons and neutrinos, all interacted together in a high-temperature plasma. After quark-gluon plasma, we have the hadron epoch. This is when quarks, these fundamental particles, combine into protons and neutrons, so the positively charged and the neutrally charged particles that later on form atomic nuclei. And finally, we get to the photon epoch, which lasts about 380,000 years after the Big Bang. This is when atoms finally form and photons decouple, and so the cosmic microwave background is created. Another way of describing inflation is the invisible thread between quantum gravity. So at the very beginning, when we talk about grand unification epoch, or when we talk about Planck time, where gravity is not yet unified with the other forces and we need quantum gravity to describe it. So inflation separates between quantum gravity and the observable universe, so what we see in the universe today. And in this episode, we'll walk through its mechanics, the problems it solves, and the clues that it leaves behind. The first problem that is solved by the inflation is called the smoothness problem. Imagine you're looking at the night sky and you have a thermometer in your hand. And no matter where you point it, left, right, up, or down, you always get nearly the exact same reading, which is 2.73 Kelvin. Kelvin here is a unit of measurement of temperature. And that is the temperature of the cosmic microwave background, the oldest light in the universe, which dates back to about 380,000 years after the Big Bang. So here's the big mystery. In the standard Big Bang model, without inflation, the universe didn't have enough time for light or heat to travel from one side of the universe to the other one. So how did these regions know to match their temperatures? How come all these regions of the universe have the same temperature? How do they reach what we call thermal equilibrium? This is called the horizon problem. The idea is that regions we observe in the cosmic microwave background are beyond each other's causal horizon, which means no signal could have traveled between them since the beginning of time. Yet, they appear identical. Now, this is really crazy. Imagine you look up at the night sky, you're measuring the temperature of the universe, and it's always the same in every direction. You measure the temperature of the cosmic microwave background, this primordial ancient light that came from 380,000 years after the Big Bang, and you're getting the same signal from every single direction. How did this happen? How is it that everything is identical? And this is where inflation comes in. It solves this problem, or maybe it's not a problem, but it solves this mystery by suggesting that all those regions were once in contact in a tiny patch of space that was in thermal equilibrium. Then, during a brief and violent burst of exponential expansion, that tiny smooth region was stretched out to include the entire observable universe. And that's why the cosmic microwave background looks the same everywhere today. Without inflation, this level of uniformity is a coincidence of shocking proportions. With inflation, it becomes inevitable. So to explain very quickly, we're basically saying that what inflation does to explain this coincidence is it says everything started off at the exact same point that was at thermal equilibrium, and then that point expanded. And because they were technically all connected, all these points, because our universe was somehow this one, small state, this one point where everything was connected, then it would make sense that even after it expanded, all these things, for example, the cosmic microwave background, the temperature is identical no matter where you look. Because once upon a time, long, long time ago, everything was technically connected before it expanded. The second, let's call them coincidences, because calling them problems is too negative. So the second coincidence that inflation kind of explains is called the flatness problem. So in general relativity, the geometry of space depends on the total energy density of the universe. So the geometry of space, the shape of space, of the fabric of space, depends on what the universe is made of. A universe that has too much energy density curves inwards like a sphere, so a three-dimensional circle. We call this a universe that has positive curvature. If it has too little energy density, then it curves out like a saddle, like what you put on a horse or a camel. And we say that this has negative curvature. And it is only when the energy density is exactly equal to a certain value, like a very specific value, which we call the critical value, do we get a flat universe, which is what we live in today. And so here's the issue. Flatness is unstable, right? Living in a flat universe is a problem because any small deviation from flatness in the early universe should grow with time. Yet, the universe is flat to within 0.1%. So now, when I say the universe is flat, please keep in mind, I'm not saying the Earth is flat. These are two very different things. I'm not talking about a planet. I'm talking about the universe itself. I'm talking about the fabric of space-time. So our universe today is flat to within 0.1%. And this doesn't make sense because if you have any small deviation, if you have any small bumps in this flatness, in the early universe, you would expect them to grow over time, but they haven't. So this suggests an extreme fine-tuning of the initial conditions, unless something dynamically drove the universe towards flatness. And that something, once again, is inflation. So as space expanded exponentially, any initial curvature or any bumps that may have started in the beginning of time, in the beginning of universe, got diluted. They got smoothed out. That way, zooming into a very small patch on the balloon makes it look flat. inflating the universe smooths out any curvature. By the time that inflation ends, the universe looks flat regardless of how it began. So it's like if you have this balloon, or if we have our, thermally at thermal equilibrium point, our balloon, and even if it had these like small bumps at the early stages of the universe, if you blow air into the balloon, if you watch it expand, eventually these bumps kind of get smoothed out and everything becomes flat. And this is what we're saying that inflation did. We're saying that inflation solves the fact that we see a flat universe today, and it solves the fact that if there were any deviations in the beginning of the universe, then inflation would have also smoothed out those deviations. It would have smoothed out those bumps, so we don't have this issue of not having a totally flat universe, because we do. The other problem that inflation solves, and it's not the second problem or the second coincidence, it's like the second problem and a half, which we call the dipole problem. And this is like a little clue. It relates back to the cosmic microwave background. So we call this the dipole anisotropy of the cosmic microwave background. And it refers to a pattern in the sky where one hemisphere, so one side of the cosmic microwave background, is just a little bit hotter, and the opposite side of the cosmic microwave background is a little bit colder. And this measured difference is about 3.36 millikelvin. So before I was saying that the cosmic microwave background has the same temperature throughout, which is about 2.73 Kelvin. Now I'm saying that actually there's two sides of the cosmic microwave background, two hemispheres, and one is hotter than the other side, and the difference in temperature is 3.36 millikelvins. So it's like a very small difference in temperature, but it's still there. So this pattern comes because the Earth, the planet that we live in, and everything that's in our local group is moving relative to the rest frame of the cosmic microwave background at about 370 kilometers per second. So things move, okay? Things are not static in space. The Earth that we live in, the Earth that we are observing things from, moves relative to the rest frame of the cosmic microwave background. So if the Earth is moving and we're observing the CMB from here, but we're relative to the CMB, which is not moving, even if we are moving, then the speed that we are moving faster than the CMB is 370 kilometers per second. The photons in the direction of motion are compressed, leading to a blue shift. So I may have spoken before a little bit about redshift and blue shift. So redshift is when you have particles of light when they are losing energy, but they cannot lose energy by losing speed, right? So they lose energy by extending their wavelength, which makes them more redshifted. So they seem, gives them this kind of reddish color. The opposite of that would be if photons, these particles of light want to gain energy, and so they shorten their wavelengths, and this makes them more blue shifted. So the photons that are in the direction of motion are shortened because they're gaining energy, and they become blue shifted. So dipoles, these, differences in temperatures, are simple but really powerful because they describe a system with two poles or two extremes, like how we have one hemisphere that's really hot and one hemisphere that's really cold. And here I refer to the hemispheres of the cosmic microwave background. So the dipoles describe a system with two poles or extremes, up, down, hot, cold, positive, negative. And in this case, the dipole is caused by velocity. It's caused by the relative movement of the Earth to the cosmic microwave background. It's motion through an otherwise isotropic radiation field, and it creates a measurable asymmetry. So here's the deeper puzzle. Why does the cosmic microwave background provide a consistent isotropic rest frame across the entire sky? How did regions so far apart in space and time come to define such a coherent, such an understandable reference frame? And again, inflation answers this. The entire visible universe, the entire universe that we can see today, came from a causally connected region. The same way that we were able to solve the first coincidence, the smoothness problem, when we said everything started off from the same point, everything was causally connected, we explain here again to sort of explain the dipole problem. that region had a uniform temperature, structure, and rest frame. Inflation took that uniformity and stretched it, imprinting coherence on a cosmic scale. And that is why the cosmic microwave background looks so symmetric, and why we see a clean dipole, we see a clean, up-down difference in poles, hot, cold regions, instead of a more chaotic motion pattern. So at the beginning of the episode, I kind of said that inflation is a scalar field. So what exactly is a scalar field? In physics, we say a field is something that has a value at every point in space and time. And the most familiar field is probably the temperature in a room. You can assign a temperature to every point in space and time around you, and that's a scalar field because temperature is just a number. It's a scalar. So that's what scalars are. They're numbers, they're values of something. And so scalar fields differ from vector fields like wind or magnetic fields because vector fields have both a direction and a magnitude. Where scalar fields only have a value, a temperature of a room only has a number, but a vector field like wind or magnetic fields can have a number, but they can also have direction. A scalar field is much simpler than that. It's just a number, like pressure or temperature, but it varies from point to point. In cosmology, scalar fields carry a lot of energy and drive profound changes in the structure of space itself. The inflaton is a theoretical scalar field, which means it's described by a single value at each point in space. It's believed to have dominated the energy content of the universe during the inflationary epoch. So during this, time when I was explaining the timeline, this inflaton field dominated the energy content of the universe. It doesn't push, it doesn't pull in any particular direction like a magnetic field would. Instead, just the fact that it's present, its mere presence and energy density cause space to expand. So this field is governed by a potential energy function, which you can think of like a landscape. Picture a ball that's rolling along hills and valleys. If the ball is sitting high at the top of a mountain, it represents a state of high potential energy, right? In this state, the inflaton field drives inflation, the rapid exponential expansion of space. So let me say that again, because I think this part here is a little bit complicated. The inflaton, this scalar field that we use to describe inflation, is described by a single value at each point in space. And it dominated the energy content of the universe during the inflationary epoch, right? So the sort of metaphor that we're using today is a ball that's rolling along hills and valleys. If a ball is sitting at the top of a mountain, at the very top, at the peak, means it's at a state of high potential energy. And so at this state, the inflaton field drives inflation. But eventually, the ball rolls down the hill or tunnels through a barrier to a lower energy state. So now it's at a lower potential energy state. And this process can happen slowly, and we call this slow roll inflation, or it can happen suddenly. Here we talk about quantum tunneling, which is a term you may have heard before. So quantum tunneling is kind of like a magic trick that's done by the quantum world. It allows the inflaton field, or it allows the inflaton to instantaneously shift to a new state by crossing a barrier it couldn't classically overcome. So to cross a barrier, or to, cross a barrier, yes, classically, would be if this ball rolled slowly down the hill. But quantum tunneling allows the ball to tunnel through a barrier to a lower energy state. And this happens not classically, which is why we call it quantum tunneling. So once the ball reaches the bottom of the potential, once it's at the bottom of the hill, the inflaton field oscillates. Here, when we say oscillates, you can kind of think of like a clock, or you can think of a ball at the end of a string that's moving back and forth. So the inflaton field oscillates, it moves back and forth, and then it decays, it breaks down, and it releases its energy into particles and radiation. And this, once again, here I'm describing reheating, which it marks the beginning of the universe as we typically understand it. So first we have inflation, this rapid exponential expansion of the universe, then we describe this inflation using a scalar field called the inflaton. This oscillates, it moves back and forth, and then it breaks down, so it releases its energy into particles and radiation. We call this reheating, and that is the moment when the universe becomes what we typically understand it to be, this hot, very dense state that leads to stars, galaxies, and cosmic evolution. It leads to the matter that we see in the universe today. So I'm going to stick to this, ball at the top of the hill metaphor to describe a little bit more about inflation. So how can we describe the specific shape of the inflaton's potential? We say, how steep is the hill? How wide is the valley? Are there cliffs or plateaus? All of this affects everything. For example, it affects how long the inflation lasts and what kinds of quantum fluctuations occur and what signals we see today in the cosmic microwave background. And this is what I'm saying. Everything in our universe is connected because inflation tells us that they were all causally connected at some point in time before the beginning of everything. So I'm going to explain a little bit more about what inflation is, or how it's driven by the scalar field. So this scalar field is in fact a scalar quantum field, and this field dominated the energy content of the early universe, and it acted like a cosmological constant, but only temporarily, only for a short amount of time. So the behavior of the inflaton, the scalar quantum field, depends on its potential energy. So whether it's at the top of the hill or at the bottom of the hill. So in many models, the inflaton sits in a local minimum, which means it sits at the top of the hill. And here we call this a false vacuum, where the energy remains constant. So here we use a kind of technical term. We say the universe is dominated by vacuum energy, which is what leads to this exponential expansion. So eventually the inflaton transitions to a lower energy state. It's at the bottom of the hill, and this can happen slowly or it can happen suddenly. Like we said, if it happens suddenly, then it's quantum tunneling, and it's like a ball spontaneously appearing on the other side of a hill without rolling over it. So it kind of just teleports. And so after the inflaton decays into the true vacuum, so after it decays into all the particles and the radiation, this ignites the hot Big Bang and fills the universe with the matter we see today. And once again, the details of the inflaton potential, its shape, its steepness, and its symmetry determine the duration and properties of inflation, including the spectrum of fluctuations we observe today. And if you remember, then fluctuations are the beginning of matter. Quantum fluctuations at the beginning of the universe were the seeds of galaxies and stars and all the matter that we see in our universe today. So, quantum mechanics tells us that even empty space isn't really truly empty after all. Fields like the inflaton show tiny fluctuations due to the Heisenberg uncertainty principle. So in case you didn't know, the Heisenberg uncertainty principle is one of the weirdest but most important and core ideas in quantum physics. In simple terms, Heisenberg's uncertainty principle says you can't know exactly where a particle is and exactly how fast it's moving at the same time. The more precisely you measure one, so the more precisely you measure, for example, where it is, the fuzzier or the less certain you can be about how fast it's moving. This is built into the universe itself. Particles don't have both an exact position and exact momentum at the same time. Reality at the smallest scale is inherently fuzzy. So I'm going to say this again because it's so freaking cool. Quantum mechanics isn't just a measurement problem. This is something that is built into the universe itself. Particles don't have both an exact position and exact momentum at the same time, which means reality, the makeup of our universe at the very smallest of scales, is inherently fuzzy. It's not specific. So due to the Heisenberg uncertainty principle, fields like the inflaton have these tiny fluctuations. And during inflation, these tiny fluctuations, we call them quantum fluctuations, were stretched to very, very large cosmological scales. A fluctuation that started off smaller than a proton's width could, after inflation, span the same width of a galaxy cluster. So a fluctuation, a tiny bump that started off smaller than a proton's width, after inflation ends up being the same size as a galaxy cluster, so a collection or a group of galaxies together. Once the expansion pushed a fluctuation beyond the horizon, and here horizon refers to the limit of causal contact, it effectively froze. So after expansion, after inflation, pushed a fluctuation outside the limit of causal contact, outside the limit when everything was connected at the very beginning of time, it effectively froze. Its amplitude became fixed and the fluctuation transitioned. It went from being quantum to classical. And after inflation ended, these frozen ripples, these frozen bumps, these frozen ripples, these frozen bumps, they became real. They went from being quantum to classical. They became real, measurable differences in density. Where there was slightly more energy, gravity began to pull matter together. Where there was slightly less energy, matter diffused away. And these ripples grew over billions and billions of years into stars, galaxies, and cosmic structure. And here I just explained how tiny quantum fluctuations due to inflation became what we see today as stars, galaxies, and cosmic structure, the large-scale structures of the universe. And inflation predicts that these fluctuations should be scale invariant, which means they have the same amplitude across all their sizes. And that is exactly what we see in the power spectrum of the cosmic microwave background. The slight departure from perfect scale invariance, a tiny tilt, also matches predictions, and it helps us constrain inflationary models. We even observe that the fluctuations are what we call nearly Gaussian, meaning their statistics, if you plot their statistic, it follows this kind of bell curve, which is consistent with random quantum origins. And that is the origin of structure, the moment the quantum became the cosmic. Now, let's once again hop into our time machine and rewind to the late 1970s. Physicists were wrestling with the unsolved problems in cosmology. The Big Bang Theory explained a lot, but it left a lot of key puzzles untouched. For example, the horizon problem, the flatness problem, and the absence of magnetic monopoles. The universe looked too smooth, too flat, and too clean. There was no mechanism to explain why. Enter here Alan Guth. In 1980, while he was thinking about grand unified theories and the mystery of missing magnetic monopoles, Guth realized that a brief period of exponential expansion could solve all of these problems in one blow. He called it a spectacular realization. But Guth's model, based on a sudden drop from a false vacuum, had problems of its own, particularly the graceful exit problem. It was hard to make inflation end in a smooth and consistent way. Then came Andrew Lind, who proposed new inflation, which caused a more gradual transition. He later on went to introduce chaotic inflation, a model where inflation could begin from a wide variety of initial conditions, making it more robust. In Lind's view, inflation was a general feature of the early universe, not a coincidence. And so these models laid the foundation of what is now a central pillar of modern cosmology. Inflation is not just a theory. It's a paradigm shift that redefined our understanding of cosmic genesis, the beginning of time, the beginning of the universe, the beginning of everything. It rewrites the Big Bang as a local event, a thermodynamic consequence of a phase transition within an inflating background. From this perspective, all structure in the universe, from galaxy clusters to the cosmic microwave background anisotropies, arises from quantum fluctuations in the inflaton field. And so these fluctuations, once subatomic in scale, were inflated to astrophysical sizes and became imprinted in the metric as curvature perturbations. The power spectrum of these perturbations, nearly scale invariant and Gaussian, matches really well with observations from missions like WMAP and Planck. Theoretical models of inflation are diverse, there's a lot of them, and they're still under active investigation. They include slow roll inflation, hybrid inflation, eternal inflation, and warm inflation, and finally brane inflation. Each one of these models has different predictions for the spectral index, the tensor to scalar ratio, and non-Gaussianity. And inflation also invites us to confront deep philosophical and physical questions. If spacetime itself is emergent and inflation is an eternal or metastable phenomenon, then the universe may have no unique origin. It may still be beginning, somewhere beyond our cosmic horizon. And so next time, we'll turn to one of the questions inflation doesn't fully resolve. What, if anything, preceded spacetime? And is the beginning even a meaningful concept in quantum cosmology? Until then, stay curious and keep exploring the cosmos.